Thank you so very much, Justin. Thank you all for being here, and I'm going to just dive right in. So, Mike Borowczak over in ECE, and let's move forward. So, quick background: graduated from the University of Cincinnati in 2013. Did some industry work, Texas Instruments, Cincinnati Children's Hospital, Intel, a couple startups, before returning to academia in 2018. Some of that industry work overlapped with educational time, so didn't fit all 5 of those jobs in 5 years. Academia-wise, University of Wyoming was the Loy and Edith Harris Assistant Professor of Computer Science, followed by the Templeton Associate Professor of Electrical Engineering and Computer Science. Senior member of IEEE and ACM. Also do quite a bit, as was alluded to in the bio originally, with engineering education. Currently serve as the program chair for the 2025 conference of the American Society of Engineering Education, program chair for the Computers in Education division, which I suspect many of you have intersection with at some point, so would love to discuss that further with any of you. Also serve as the editor-in-chief for the journal from that same organization. And I recently became the campus representative for UCF. Big part of my job is also joint appointment with Department of Energy's Idaho National Labs, and you'll see some of the intersection of that work in this presentation. So quickly, by the numbers, currently at UCF, I did join about 18 or 19 months ago in fall of 23 as an associate professor. Currently, lab features 11 graduate students, 15 undergraduate researchers. Over my time since 2018, I've graduated 3 Ph.D., 9 master students, quite a bit of funding. Currently here at UCF, 3 industry partners, AMD, Arctic Wolf Network, and Northrop Grumman. But you'll see, and hopefully you'll get a sense of it, that I try to diversify my funding streams across several different areas. I bring this up really because this presentation tries to capture some of the work that has been done, but that work is definitely not possible or would not have been possible with a lot of support from others. And so the big driving force is often our graduate students and undergraduate researchers. So just bear that in mind. This is not just my work. This is really work of a much larger group. So really what we're talking about is the fact that a lot of our devices that we operate and use, actually anything, contains significant information-rich channels. Now, historically, people have been focused on taking specific data elements out of these channels. We'll talk about that here in a second. But I want to mention that the prediction about a source without direct access to the source, it's really not a new challenge at all. If you think about all of the work that has happened in terms of astronomy, physics, but if you even think about what we know about the human body, there are many times that we make inferences about how a system is operating based off of byproducts of information. So what you actually see on the right-hand side in that purplish picture is the very first EKG, electrocardiogram, from the late 1800s. Right? So starting to investigate, say, measures of electrical signals from the heart to make inferences about how the heart is operating. It's today we take it for granted, but realistically, that's what we're talking about here, is using secondary sources of information from a system to infer properties of that system. So that requires creating models of systems, comparing models to measurements of the system, and that measurement is key. The granularity, the fidelity of the signal that we can capture in a system enables us to perhaps extract more information, depending on what we're looking at. And ultimately, our goal, in the research that I do, is to predict properties, generally hidden properties of the system. So some things that we use, we differ from a lot of other researchers in this space, but we focus on information theory. We look at where we think that system has great entropy or state changes. We use applied statistics for a large majority of our work. There's been a recent push, as with a lot of fields, to also use AI and machine learning. ultimately, the way that we are able to attack, or I'll say explore, the interconnection between data and information and a system is by locating or having some sense of where operations that a system is doing and data come together. Where are those critical areas of interest? The other thing that we take advantage of is that even if we design very complex theoretical transformations on information, when we implement those, whether it's through an algorithm or in hardware, there is a transformation that occurs from the pure mathematical space into reality, into a physical system. And so one of the things that we do is we look for those opportunities of where that must occur, and we use that to our advantage to basically break or infer information within systems. So in a nutshell, bottom of the screen here, the lab that I'm a part of here at UCF, we assess, exploit, leverage, and protect information-rich side channels in hardware, software systems, from basically gates all the way up to the distributed systems themselves, and we'll take a look at that here. Before that, I want to highlight that information leakage is kind of a broad term. The question that I ask is, what is more valuable? And this is actually a loaded question because the answer is it depends. Is it the raw information, for example, is it that my heart is beating at a certain rate, right? Or is it how it's beating, right? So it's basically internal data versus process. So from an algorithmic standpoint, do you care about the algorithm or do you care about the data that the algorithm is processing? Well, historically, and so where this field started in side channel analysis and attacks, it started because we wanted to exfiltrate secret keys, data, raw data. And so that's actually been I will say the focus of much of the work for many researchers over time. Extracting secret data, extracting encrypted data in one way or another. In the AI machine learning space, being able to figure out embedded training data that is stored within a model, within a realized system, again, focusing on exfiltrating intellectual property or internal data. Where our work starts to extend beyond that is we are now interested in what else is of value. And what else is of value is all the intellectual property that might not exist as raw data, right? It is how we process information. You can imagine that the amount of money that goes into training next generation models, that takes a significant amount of time and resources. It would be dangerous if somebody could take, say, an edge device, a device that anybody has access to, and could reverse engineer the construction of your very expensive model, right? So really this is the key here. So let's take a look at a couple of examples from our lab. On the left-hand side, we have a few works that were basically funded by Department of Energy, INL. In 2023, NIST released a handful of candidate algorithms, actually algorithms that they were saying were good to go for lightweight cryptography. 2 years earlier, a team consisting of a lab that I was in, as well as a lab from Boise State, as well as Idaho National Labs, had basically shown that we could break all of the known candidate algorithms within 50, basically, iterations, 50 clock cycles. And this was known to be a risk. So definitely feasible. Moving on, similar vein, but completely different target, moving away from trying to exfiltrate data and exfiltrate properties of systems. Again, Department of Energy, Idaho National Labs, wanting to understand if it was feasible to attack models that were running on edge devices, specifically to figure out what models were running, as well as, say, very large, basically parameters of those models. So work here existed on essentially reverse engineering based off of power consumed of a device, what type of machine learning model, as well as some of its larger parameters. For example, in a neural network, how many nodes, linear regression, lambda feature. Again, very large, I'll say, gross properties of the system. Move that to the right-hand side, and we start to explore other spaces where this also has interest. Can we take two devices and characterize changes? Can we look at power consumed and detect additional circuitry, additional logic that shouldn't be there? And so we have work that also has done that. Now, where we're bleeding into right now is novel technologies. So memoristic devices, say, are a pretty interesting space. We actually happen to have one of the only known commercial memoristor devices in our lab. And so we are now also exploring if the attacks and the limitations, risks that traditional CMOS devices have, if those also exist within novel technologies. So this is really just painting a large picture. I'm keeping an eye here on time. So other spaces that we look at, I mentioned that we do this all the way to the system level. We've done this for attacks on the Paradix drone swarm. If you take a look at video released from the Department of Defense, there are some interesting behaviors that swarm has. We replicated those behaviors, modeled those behaviors, showed that those behaviors could actually lead to image C here, corralling of agents. So there's risks involved. And so then we found ways to essentially build in resilience into that system, basically through the addition of entropy, entropy of movement. So not towards the original objective functions, but to basically solve this risk. All right, really quickly, last 2 minutes that I have here. My statement here is that none of this matters if we don't have a future, I'll say, technology literate workforce, right? Who is going to be operating the processes of tomorrow, right? The technology and infrastructure of tomorrow. Who's going to understand how to control the devices in their homes, businesses, environments, research labs? Who's going to engage in research, right? Who are we going to have as future researchers, let's say 5, 10, 15 years down the road, right? I will say that I know many of us are interested in how do we engage in, let's say, K-12, right, pre-collegiate students. But having looked at this problem for the last 20 or so years, there is a bias that many of us have. We look at things from a deficit perspective and a kind of a, we can save this group by doing just these things. So, you'll hear statements like students, teachers, schools lack something, or they need something, or not enough time is spent. We frame things as, well, students and teachers just need to do something and it'll fix everything. I'll teach them by research. I will teach them blank, and they will immediately understand things. And that's, we found, not the case in general, right? So teachers have a finite amount of time. They have to follow pretty specific plans. They're asked to do more and more things, right? So inclusion, for example, of computer science into curriculums is something that has happened across the US. But how do you do it with a finite amount of time? They have to compress things. They basically end up cutting things that are best known pedagogical processes. So they're forced to do more. So they have to do perhaps less things along the way, right? They can't focus on all the best known practices if they are forced to do more things. So what we've done for the past about 20 years is we have focused on meeting educators where they are. Right? Not trying to level up every educator, every K-12 educator we meet to a certain point, but say, you're all starting at different points. What can we do that will enable you to essentially do your job without adding extra, I'll say, burden? And really what we focused on is cross-cutting concepts. If you take the time, it is possible to find areas of intersection and overlap between what you're doing and what someone else is doing. It takes time, right? But somewhere there is some commonality. And again, it takes time. It is not a trivial exercise, especially if you are entering a room full of, say, 15, 20, 30, 100 different educators that are coming from different backgrounds. It is not a trivial task. But we found the most success that way. What this has led to, here are 4 different projects funded by NSF, basically NSA, DHS, that has resulted in, I would say at this point, well over 1,000 educators, different levels of engagement and involvement. but then contribution from those educators of over 300 lessons that were created by them for other educators, all available for free. And usually many emails of, when are you doing the next one, right? So it's, I don't know, something to consider. I know that was really quick. I want to be cognizant of time and move on to questions.